Welcome back, and today we're going to be looking at metals, what type of bonding they undergo, and their properties. One of the reasons that we want to look at bonding in chemistry is because the bonding between atoms in a substance determines the substance properties. So when we talk about properties, we can talk about physical or chemical properties. And in the case of physical properties, we're talking about, are they a solid at room temperature? What's their melting point or boiling point? And things like that. How they look and how hard they are. The other properties that we can talk about are our chemical properties, and that talks about what kind of chemical reactions they undergo and how quickly. So all bonding, be it metallic, covalent, or ionic, is electrostatic. That is, comes about due to the attraction between positive and negative particles, or positive and negative charges. Okay, so we should remember that positive and negative charges, okay, attract. So opposite charges attract, and then like charges will repel. So when we form an ionic bond, most of the time we're looking at which bits are attracting to each other to stick the substance together. Okay, if they repel, then that's not going to help keep it together. Okay, so metal is any element that loses its outer shell electrons becomes stable. So we pointed out that these tend to be towards the left-hand side of the periodic table. Okay, group 1 and group 2 are very reactive metals, transition metals in the middle, and then over onto the right-hand side, underneath the step, we have our metalloids under here, and then we have non-metals. Okay, so neutral atoms will have equal numbers of electrons, okay, and protons. So electrons are our negative charge, protons are our positive charge. So when an atom loses electrons, it becomes positive. So we tend to see positive ions or cations being formed with metals. Okay, so we have positive cations when metals lose electrons. Okay, so metals lose electrons to gain that stable octet. So when we look at metals, you should be able to think of things like a spoon or a tap, a pot, these kinds of things. These show the typical properties that we expect for metals. That is, they're good conductors of electricity, which is why we use them for wires in electronics. They conduct heat well, hence why we use them for cooking pans. They're lustrous, okay, which means shiny. Okay, so they're reflective and reflect light back. Okay, malleable, which means they can be hammered, bent, or rolled into any desired shape without breaking. They have high melting points and high boiling points, which lets us know that the bonding is strong. Okay, because it takes a lot of energy to make it melt and to disrupt those bonds. And they have high densities. And this is one that you may not remember, but we can say that density is equal to a measure of the mass divided by the volume of substance. So how much mass it weighs divided by how much volume it has. One example density would be water, which is approximately 1 gram per milliliter. So for every gram of, for every milliliter of water, it would be about 1 gram of mass. So if you often carry a 1 litre drink bottle with you, that's 1,000 milliliters, so you would be carrying 1,000 grams or 1 kilogram. So nearly all metals are solid at room temperature except for our friend mercury, and gallium has quite a low melting point. Gallium will melt in your hand. Its melting point is around 36 degrees, about body temperature. Okay, so the properties that we can see in metals allow us to tell a little bit about their structure. Okay, so we know that they conduct electricity in the solid state, so even as a solid at room temperature, they will allow electricity to pass through them, okay, from a if we connect a battery up, it will allow electricity to pass through it. So in order for electricity to be conducted, it has to have moving charged particles. So this lets us know that something within the structure of the metals is charged and able to move freely. They're malleable and ductile. So we said malleable was able to be hammered. Ductile is able to be pulled into wires. So we know they're malleable and ductile. This means that the forces between the particles are able to adjust, okay? Which means if I hit a piece of metal with a hammer, it dents. We don't break the bonds, they just move around. They have high density, so the particles must be closely packed together, and that they have high boiling temperatures, so they must be held together quite strongly. Metals are lustrous and reflective, which means there is something that bounces the light back to our eyes. Okay, so from all of these observed characteristics, we can build a model of what we think the bonding looks like. And this is what it is. So they've had a look at metals under X-ray crystallography, and what they've seen is that there is a lattice structure, okay, so which goes on in 3 dimensions. Okay, so a lattice is something that is not discrete, it's not on its own, it's something that continues on in all 3 dimensions. Okay, so it just grows continuously. So with that, we can draw this in a simplified way. Okay, so the model of the metallic bonding that we want to understand is that we have metal cations. Okay, so this is our metal atoms. Okay, and they have donated their valence electrons out into this delocalized sea. Okay, so there's still one metal atom and with its right number of electrons, so it's neutral overall, but in the lattice we have metal cations, okay, so because they don't have their electrons around them straight away. So these are metal cations, and then these electrons, this delocalized sea, is made up of the valence electrons from the metals, okay, but overall the entire piece of metal is uncharged. Okay, so if we are holding a spoon, that spoon is going to be made up of uncharged metal ions because the electrons and the cations all balance each other out. Okay, so when we're asked to draw this, we should draw circles like oranges being stacked at the grocery store. Okay, this would be our diagram of a metallic lattice. We would put the charge of the pot of the metal inside our diagram to say that we understand their metal cations. We would draw a few electrons around it to indicate the valence electrons, and then because all scientific diagrams must be labeled or annotated, okay, we will tell the person what it is our diagram means. Okay, so we're going to label each part of our diagram. So we would write a 3D array, or you could use the word lattice of metal cations, and then our electrons are our sea of delocalized valence electrons. Okay, so we're indicating that we understand it's 3-dimensional. We don't have to try and draw in 3 dimensions. We just need to state that we understand that it is, and that this free-moving sea of electrons is running around in between our cations all the time. This means that the force of attraction, that electrostatic attraction, extends in all directions and stabilizes our lattice. Okay, So this is the diagram again, remembering that the positive ions are called cations and they're in fixed positions. So they just vibrate in space, but the electrons move around the cations, zipping in and out, making sure that those cations don't have positive to positive interactions. So they're constantly surrounded in a little cloud of negative charge. Okay, so low electronegativities on atoms means that they aren't able to draw electrons to themselves very well. Okay, so they tend to lose their outer shell electrons easily, becoming positive cations. Okay, so these electrons, okay, the cations have all their electrons other than their valence shell electrons sitting around their nucleus while they're in the lattice. Okay, it's only their valence electrons that are free to move throughout the lattice. So the electrostatic force is the attraction between the positively charged cations and negatively charged electrons, okay, the delocalized C, and that holds our lattice together. That's all I want to say on the structure of the model. You should be able to draw an example of the model and label it and annotate it clearly. In our next video, we'll talk about the properties.